Okay, this is discussion 11.1, sort of an introduction to medicinal chemistry, and then we're also going to talk about pH regulation of the stomach. So in your textbook and in the guide, this is topic D1 is the introduction, and D4 is the pH regulation of the stomach. So if you're looking in the textbook for more information, that's where you should go. All right, so what is medicinal chemistry? It's a cross-disciplinary science, and the whole goal of medicinal chemistry is to discover, design, and develop new bioactive compounds for therapeutic use. So we're just trying to find new treatments that work in the body. Pharmaceutical drugs are compounds that can prevent or cure diseases, alleviate symptoms, or assist in diagnosing illness. Now, an interesting thing about some drugs and sort of the way the body handles drugs and illness is that we don't always understand the mechanism of how certain drugs work very well. So for example, we know that the body can be tricked with the placebo effect. So the placebo effect is demonstrated when somebody is given something like a sugar pill but told that it's a medication that will help their illness and their symptoms still improve. Now, one of the things we can do to tell if it's present is use double-blind studies. So in a double-blind study, we would have a group that's receiving a placebo and a group that's receiving the actual drug in question. And neither the people receiving the drugs nor the people administering them would know who was who, if that makes sense. So in that way, we can find out if the placebo is having an equal effect as the drug. Now, this is sort of an interesting ethical issue because there's an aspect of dishonesty that we worry about with people not knowing what they're taking, what they're not taking, but it also is really valuable in helping us understand what's actually improving the person's condition. So when we develop medicines, there's several major phases. Research, so first we have to identify the need and the structure. So we need to identify the site of activity in the body that we're trying to target and then develop the drug structure intentionally. So for example, if we're trying to block a certain receptor, it would help to know what kind of molecule normally binds to that receptor. We have to synthesize the drug and then get the yield of the drug and then extract and purify it. So when we're going through that synthesis process, we obviously want to find a synthesis that will give us a really high yield of the drug with as little waste as possible. Now, there's a lot more detail on this in the book, and I would really suggest that you read it. Pages 721 to 723. So take a look at that just to give you a little more context for this. Now, in the development phase, we have to do testing. So the first thing that usually happens is testing on animals, and we're determining two things. The first thing would be the LD50, and that's the lethal dose required to kill 50% of the animal population. Now that probably bothers some of you, and that is understandable, and this is a big ethical issue in medicinal chemistry, is to what extent is it acceptable to test drugs on animals for human use. We also would do a determination of the ED50, and that's the minimum effective dose that's required to bring about a noticeable effect in 50% of the population. So together, finding those two things will allow me to determine the therapeutic index, which is the ratio of the LD50 to the ED50. Now, we'll talk in a minute about why this is, but the higher that ratio is, the better, right? If the ED and the LD50 are very close to each other, that may not be the greatest drug. So after it goes through animal testing, we would have human testing. Now, rather than determining the lethal dose for obvious ethical reasons, we would determine the toxic dose for 50% of the population. So the therapeutic index in humans would be the ratio of the toxic dose, TD50, to the ED50. And in this particular case, when we say toxic, we mean that it has an unacceptable adverse effect. Now, what is unacceptable may depend on the pharmaceutical product and what it's meant to treat, right? If you're trying to treat something like cancer, certain adverse effects may be more acceptable than if you're trying to treat a headache. So if my therapeutic index is 100, what does that mean? Well, it means that the ratio of the toxic or lethal dose is 100 times the effective dose. So that's a pretty good window. Now, the therapeutic window is the range of doses where the drug provides the desired therapeutic effect without unacceptable adverse effects. Okay? So the larger that therapeutic index, the larger the window as well. This is sort of a more vague range than the therapeutic index. the therapeutic window would sort of open before the ED50, because remember, that's the amount that's required to produce a noticeable change in half the population. So some people may not require that much, and it's going to close a little bit before the TD50 because we don't want to get so close to the toxic dose that there are a lot of unacceptable adverse effects. Now, when we think about what's more desirable, large or a small therapeutic window, a large therapeutic window is much more desirable for a couple of reasons. Well, for the first, it's harder to accidentally overdose, right? If the toxic dose is 100 times the effective dose, that's unlikely to happen accidentally. And then there's also more room for variations in dosing, since different members of the population will need different doses to have effectiveness. However, there are circumstances under which a small therapeutic window would be acceptable, and I'm sure you can think of some, right? If you have a serious or life-threatening condition that needs to be treated aggressively and quickly, then a small therapeutic window would be acceptable. So some examples off the top of my head are anaphylaxis, or if you're trying to treat cancer, right? If someone's having an anaphylactic response, they need an immediate, fast-acting drug, and some adverse effects are probably acceptable. Likewise, if someone's being treated for cancer, chemotherapy has lots of unwanted effects and probably a fairly small therapeutic window for most drugs, but again, it's a life-threatening illness, and so a small therapeutic window would be more acceptable. Again, if you're treating something like a headache, you'd want something with a large therapeutic window. And drugs with a small window do need to be carefully monitored. A lot of times these would be given in healthcare settings. These wouldn't necessarily be drugs that people were taking at home, and if they were, it'd be the kind of thing where they were monitoring regularly to make sure there wasn't too much of the drug in your system. Now, there's a lot of different ways that medications can be administered. You should just generally be familiar with them, but the ones we talk about most are injection and oral medications. And there's different kinds of injections. There's intravenous injections, like an IV, intramuscular injections. So an example of this would be EpiPen injections are given typically in the leg muscle. Tetanus shots are intramuscular, and then subcutaneous. So the injection for the TB test, subcutaneous meaning under the skin. Now, it would be convenient if we could take all medications orally, but we can't. Okay, so there's a couple different reasons that might be. So maybe the medication is unacceptably degraded by stomach acid, or it might require faster action, okay? If something requires fast action, then we typically would need to inject it, like an EpiPen. And it might not reach the target for a bunch of different reasons that are related to something called bioavailability. Now, when we look at different medications and determine whether or not we want to use them, one thing we have to consider are unwanted effects. So side effects are non-beneficial effects on the human body. So these are things that we're not trying to have happen, but happen anyway. And anytime you ever see a pharmaceutical ad, they rattle off the side effects at the end. And we'll talk in class a little bit about how they actually come up with that list of side effects, because it's fairly interesting. Some of them are more common than others. But some of them are known and well established. So for example, aspirin can cause stomach bleeding. Now, when we decide whether or not we want to use aspirin, we have to consider something called the risk to benefit ratio. So if we have an effective treatment for a life-threatening disease, or even a disease that's causing us a lot of harm in some way or another, or degrading our quality of life, then a higher risk from side effects is more acceptable. So, for example, aspirin can cause stomach bleeding, but it's also been shown to be effective in preventing heart attacks, since it's an anti-clotting agent. It's also used sometimes in pregnant women to prevent preeclampsia, which is a really dangerous pregnancy complication. So in both of those cases, the small risk of stomach bleeding may be worth it for these people because they're preventing life-threatening events. Now, tolerance is another unwanted effect that occurs as the body adapts to the mechanism of the drug. And so when tolerance occurs, larger and larger doses are needed to achieve the desired effect. Now, there's two problems with this. First of all, there's an increased probability of dependence or addiction, and some medications seem to be more addictive than others, and some people seem to be more prone to addiction than others. And we also have a greater probability of reaching the toxic or lethal dose, which is extremely dangerous. So both of those are unwanted effects. Now, an example of unwanted effects of a drug, we talked about this a little bit in Unit 10 when we talked about enantiomers, and we talked about thalidomide. So thalidomide is a drug that is a chiral molecule and it has 2 enantiomers. And one of the enantiomers cured morning sickness in pregnant women, but the other led to really bad birth defects. So these women did experience relief of their symptoms, but it came with unacceptable side effects. So in this case, the risk to benefit ratio was not acceptable, and that's why it's been discontinued for use in pregnant women. It actually has been shown to be a pretty effective treatment for leprosy, oddly enough, but that's a different situation, and again, it wouldn't be used in pregnant women because of the risk of birth defects. Now, we talked briefly about the term bioavailability, and we talked about methods of injection. Methods of administration. So, if I take a medication orally, that may affect the bioavailability of the drug. So, the definition of bioavailability is the fraction of the administered dosage that reaches the target part of the body. Now, if I inject a drug into the bloodstream, it's considered to be 100% bioavailable. Now, there's several factors about the drug that affect bioavailability. The first is solubility. So if the solubility in water is low, a drug might have to be injected rather than taken orally because it won't be readily absorbed into the bloodstream. Polarity is another. So polar molecules that have especially carboxyl, hydroxyl, and amino groups capable of hydrogen bonding are easily absorbed into the bloodstream. However, those molecules might have a hard time crossing hydrophobic cell membranes or the blood-brain barrier. So there's multiple considerations when we think about the polarity of a molecule depending on where in the body it needs to go. And finally, the presence of functional groups, which affects polarity, and so we'll discuss that when we talk about D2 and D3 with some specific molecules and examples. Okay, so when we talk about pH regulation of the stomach, this is part D4 in the textbook, there's really 2 major ways that we can regulate the pH of the stomach. First, we can use non-specific reactions, so basically antacids. Those just generally neutralize acid directly. Or we can regulate acid secretion. Okay, so we're going to talk about both approaches and give some examples and ways that different cases or situations where they might be used. Okay, so antacids are non-specific reactions, and they just work to neutralize excess stomach acid. So I'm going to give a few examples. You'll see these, you'll see hydroxides, you'll see hydrogen carbonates or bicarbonates, and you'll see carbonates. All of those are antacids. So aluminum hydroxide reacting with HCl, which is a major component of stomach acid, produces water and aluminum chloride. Sodium bicarbonate reacts with HCl to produce sodium chloride, water, and carbon dioxide, and calcium carbonate reacts with HCl to produce calcium chloride, water, and CO2. You should be able to write equations for really any hydroxide, hydrogen carbonate, or carbonate with HCl and have a sense of what they produce. And you would also be expected to include state symbols with those. So you should be aware that the stomach is an aqueous environment, and that should help. You generally know that water is a liquid and carbon dioxide is a gas, so it shouldn't be too hard to come up with those state symbols. And most of the antacids are taken as solids. All right, so let's look at a kind of sample problem you might be given. Now, the great thing about these problems is that they're really tied into the problems in Unit 8, in 8.1, where we were doing basic calculations with moles of acid. So in this problem, we have an antacid tablet that was added to 25 milliliters of 0.125 molar hydrochloric acid. After the reaction was complete, the excess acid remaining required 5 milliliters of 0.2 molar sodium hydroxide to be neutralized. So this is a process called back titration, where we basically titrate the remaining acid to see how much was neutralized. So we can determine the neutralizing power of the tablet. Now, when we talk about neutralizing power, units are likely going to be given for what they want. There's all different kinds of questions I've seen IB ask about basic antacid calculations. In this case, let's find the moles of acid neutralized per gram of antacid. Okay, so we have to go through a few steps to do this. First, we have to find the original moles of acid in the sample. So we would take the molarity times the volume in liters, and we would get our answer in moles. Next, we want to calculate the moles of acid that remain after the antacid did its work. So after the antacid did its work, we were left with 0.001 moles. So we can use those two numbers to figure out how many moles of acid the antacid actually neutralized. Okay? So 0.002125 moles were neutralized per 0.2 grams. So then we could say that the neutralizing power was 0.0106 moles of acid per gram of antacid. And again, you could solve all different kinds of problems with this. You could find the pH of the acid before and after the antacid was added. You could compare the moles of acid neutralized by different antacids. So there's a lot of different kinds of simple acid-based problems that can be done with this. Antacids often have additives as well. So they have dimethicone, which is an anti-foaming agent to reduce bloating. Since some of these produce CO2, obviously there can be some foaming in the stomach. And alginates provide a protective layer on the top of the stomach contents to prevent reflux, which leads to heartburn. And these sort of non-specific reactions tend to be used more on an as-needed basis. Someone with chronic reflux is probably not just getting by taking Tums. Okay? So for people that have more chronic problems with reflux, they would use a different approach to pH regulation of the stomach. So they would probably look at regulating the acid secretion directly. So other drugs besides antacids that are used to regulate the stomach pH don't actually directly neutralize the acid. Some examples of these that you've heard of are Zantac. I can try to say these actual medical names, but I'm not sure I would do it correctly. Prilosec and Nexium. And these structures are in the data booklet for you. So it's near the end, table 37, there are representations of some medicinal molecules. And it's good to know that these are there because some really easy questions in the IB exam, they might just ask you to identify functional groups in some of these molecules. Okay? So we're going to talk about how these molecules work. And what sort of some advantages of them or disadvantages are. So the mechanism of action is that they're going to target the actual production of the acid in one of two ways. So they're either going to target H2 histamine receptors, or they're going to inhibit the gastric proton pump. So H2 histamine receptors, secretion of acid is triggered by histamine molecules binding to the H2 histamine receptors. So if we can prevent histamines from binding, then we could prevent some secretion of acid. So this is how Zantac works. It blocks these receptors to reduce the acid secretion in the first place. Now this is relatively short acting, longer than antacids, but a lot of times these have to be taken multiple times per day, and the effects aren't going to last for days at a time. Now the other approach is to inhibit the gastric proton pump, and that's an enzyme that's directly responsible for secreting H+ ions into gastric juice. Now when we talk about protons, remember, that's H+. So the gastric proton pump pumps H+ into gastric juice. Now, these two drugs, omeprazole and esomeprazole, inhibit the gastric proton pump. So the first is a racemic mixture of two enantiomers, but these two enantiomers do seem to exhibit very similar activity. Now the other is only one of those two enantiomers. So they're basically the same drug, but the first is a racemic mixture, whereas the second is only one of the two. And these produce the same active metabolites, both enantiomers, and these bind to the proton pump enzymes and inhibit the acid secretion. These tend to last longer than the H2 histamine receptor drugs, and the effects can last for several days. So for someone that had a really chronic condition, these might be a better choice than Zantac, which could be taken more on an as-needed basis, or certainly better than antacids. All right, and then the last piece of this pH regulation of the stomach is talking about buffers. So we already know what a buffer system is from Unit 8. As a reminder, it's a weak acid or base and its conjugate. And so we need sufficient amounts of both the acid or base and the conjugate to resist changes in pH with addition of small amounts of acid or base. Now, we haven't done this yet, but we can calculate the pH of a buffer solution using an equation called the Henderson-Hasselbalch equation, which is an awesome name. And that equation is pH equals pKa plus log of the concentration of the conjugate divided by the weak acid. Now, this is a real good news, bad news situation. The bad news is this equation is not given directly in the data booklet. So there's two approaches. You can memorize it. You can kind of think pH equals pKa plus log, aha! But then you have to remember that the ah is divided by the ha. Or, since you're all super good at math, you could just derive it from the Ka expression. Okay, so let's look at how we would do that. We know that Ka is the concentration of, assuming we're talking about a weak acid, not a base system, obviously, the concentration of hydrogen ions times the concentration of the conjugate divided by the concentration of the weak acid. So, using algebra, we could take the negative log of both sides, right? That's allowed. Then we can split the log on the right, so we can take the negative log of H plus the negative log of the conjugate over the original. The negative log of Ka is by definition the pKa. The negative log of H plus is by definition the pH. So pKa is pH minus the log of the conjugate over the original. And then I can rearrange to solve for the pH. Okay? So, let's look at the usefulness of this. So we can calculate the pH of a given buffer solution, which is relatively useful, or we can figure out how to make a given buffer solution. So let's say I need a buffer solution of pH 5.7. I can figure out what concentrations I would need for the conjugate and the original weak acid to do that. So for example, let's calculate the pH of an aqueous solution that contains 0.4 moles of hydrogen carbonate and 0.5 moles of carbonate. So our equation would be the hydrogen carbonate, which is acting as a weak acid here, and the carbonate, which is its conjugate base. And note this is a double-sided arrow because, again, this is an equilibrium system. So we would start with our Henderson-Hasselbalch equation. We can find the pKa from the data booklet, and then we just have to take the log of the conjugate over the log of the original weak acid, and we would get that the pH is 10.4. Now, if I wanted to make a buffer of a specific pH, I need to think about what kind of buffer system I want to use. So it's helpful to know when a specific buffer is most effective. So a buffer is most effective within one pH unit of its pKa. So you can look in the data booklet. I believe table, what table is it? Well, there's a table in the data booklet that has pKa's of common acids. And strength of organic acids and bases, table 21 on page 19. And so I could pick something that's within one pH unit of that has a pKa within one pH unit of my goal. And that's because I want a pretty close ratio of the acid base and its conjugate, because we need to have sufficient quantities of each to resist changes in pH. When we get too far away from the original pKa of the weak acid, we have a pretty great disparity in those concentrations, and so it won't be as equipped to resist changes in pH. Okay, my number one advice for this topic is to read the textbook for the whole option, because there's a lot of detail, and we can convey as much as possible in class and through video lessons, but the best way to get all the details is to definitely do the reading. Okay, the end.